Hello everyone. Today we have Franz Hinterleitner who will talk about his recent paper published on Archive on quantum gravity. So
Yeah, thank you for the invitation. Thanks to it, I was aware of a few mistakes before submitting it to a journal. This was quite good. And well, I should mention, I did much of this work not very recently, but before, together with a major from Hamilton College in the state of New York. So I wanted to mention him. And as a first part, I think not everybody is very familiar with quantum gravity, so I'll have to give some short introductory remark about it, so that you all know what's going on, what I'm speaking about, and then go to the model. So, well, blue quantum gravity, to be more exact, canonical blue quantum gravity. And the first part is a classical or preparation of classical general relativity. This means a split space-time into space and time. We have 3 + 1 split. We formulate general relativity like in form of a Young-Mills theory. Young-Mills. So this split means we have space-like hypersurfaces, and on these hypersurfaces we define our variables. These are priors, orthonormal basis at every point, which can be considered as rest frames, local rest frames. I, A, the A, where A is a space Y. That is a space-time index, and I is 1, 2, 3. Orthogonal index. And then, and what is used indeed are so-called fancified triads. Capital E for I is E A I. E A. So that matrix which gives in coordinate, in terms of coordinate differential. So this is one set of variables. The second set is the connection.
sorry. Now it looks like the triad and the densitized triad are exactly the same.
Sorry. It's E A I determinant A E A I. So then we have a connection for it is also split into a space and a time part. It's called the classical connection. A I K gamma A I K plus beta K I A K. Now this is a spatial spin connection for this normally spatial variables. The spatial spin connection, which is negativity, and this is derived from the extrinsic curvature, so how the hypersurfaces are embedded into a 4-dimensional manifold, and B is called the inertia parameter.
And this KA has to be with a time component to 0 r. Okay. But then, what how I can define the k?
Yeah. Drop down K. A is minus epsilon by A J U J E K A E, where K is A E is the extrinsic curvature. Here with the triad or with the co-triad, it's converted to show that it has been one spacetime index, one orthogonal index, and then this epsilon ijk is a generator of SO3. So this is a Lie algebra value one form. Essentially, SO3 generator. And well, and A, and E, A, I without this generator, between this is E, A, how canonical pairs. These are the variables. Then
And beta, is it a physical parameter? Does it affect anything or beta? The parameter you use.
let's see, parameter.
Does it affect the physics or it's just completely arbitrary? In the classical theory, if I want to describe GR.
And it has no influence on the equations of motion of the classical Einstein equations. Because are only in quantizing and definition of operators, area operators, and so. But we don't need it in the following.
And when you say real parameter, you really mean real as not
real.
complex.
But historically, the first imaginary parameter was used to simplify the Hamiltonian constraint.
But this is really real.
It's real, yeah. Later on, Emilzi and others found out it's possible to formulate the Hamiltonian constraint also in a convenient way with a real parameter. With the imaginary parameter, you formulate first complex general relativity, and then you have reality conditions, complicated reality conditions. And this you can avoid with the real parameter. And it was the merit of Thomas Tillman who found a way how to handle it, how to reformulate the complicated Hamiltonian constraint, even if it is real. To make use of the square root of the determinant. What is determinant? They found a clever way how to handle this. So, quantum states. We choose a connection representation, psi of A, in principle. But A as a connection is gauge variant and coordinates, connection changes in a not very simple way. So it gauge variant. So we prefer necessary to continue to do something with it, somehow to split off the gauge degrees of freedom. Take or not noise. along paths. Say gamma. So such a holomorphy is denoted by U, dependent on the connection and the concrete path. So if you transport something along a path, now it's two indices AB, that's a linear operator, is the path order comment or an integral along gamma. Gamma dot A is tangent vector A I tau A tau I J A E. So gamma dot is a tangent vector. This is the connection.
Connection of two.
Yeah, without this, instead of this SO3 generator, I've written here generally an SU2 generator, tau I AB is in SU2. And if J is 1/2, so the generator in the fundamental representation is I of the Pauli matrix sigma with two indices. If we have another higher representation than A and B, can be considered as collective indices for vectors, tensors, and so on. So yeah, here we have the generator, and here this is a group element. U is in SU2. In this form, if you have 1/2, so that what happens to spinor when it's transported along a path gamma or a vector or something. So also.
So this is not a closed path. There's no.
No, I think it is a closed path. In the general case, we construct spin networks. We have a graph made of edges and vertices. And so on. And to each edge, the edges are associated SU2 representations or SU2 elements in a certain representation. Which is called E in representation JE. So to each this paths. And to obtain in the end a function, a scalar function, page invariant, we have to contract these representations at the vertices with contractors or intertwining operators. Associated intertwiners or contractors. But that psi scalar and page invariant. For example, what we have here 1/2 and here also 1/2. And here's a representation 1, a vector, and here we have indices. Spinor indices, say A, here E, oh, it has indices for. How shall I say? A U, A B, and here we have a U, C, D, and here we have something U, Y, K, vector, here we have 1, representation 1, then here this intertwiner is a sigma, or tau, oh no, sigma I, T, and C. So it just contracts all indices so that no index is left over here. And we have a scalar function. The simplest case is just one loop with closed path. In this case, so the loop without vertex, without any node, then style is the trace of E integral ds gamma dot a.
And then all those contractors can be only the Kronecker deltas or the antisymmetric epsilon.
It
Right?
can be identically constructed from some value and epsilon.
In the fundamental.
In the one, yeah, when you decompose every representation into a symmetrized tensor product of fundamental representation, then you have either a graphical, this is a line going through, then you have a delta, and that's
Can you do a double line notation, maybe? Would a double line notation be useful?
yeah, it's if you choose such a graphical representation, then you take here for one double lines or for multiple lines, then the condition that it's possible at all is that you can close every line. Here or here, so it's a possibility there must be a possibility to close every line.
Can I get back to Richard's question on how the A got from having 3 indices to 2 indices? So you're contracted, I guess, with the epsilon.
Yes, it's
Yeah, you're contracted the 3A with epsilon, and then you get the 2A.
yeah.
Right.
This one has 2 indices.
Right.
And you can
Yeah, I mean,
Because it's the algebra matrix, so you can expand it on the basis of the
that's exactly my question, because it's clear that you can do that with the K, with the intrinsic curvature, because the intrinsic curvature have only 2 indices to start with.
Yeah.
But the A comes from the Christoffel symbols, and it's not completely clear that the Christoffel symbols is
Yeah,
antisymmetric.
you also dualize this epsilon. You also
But that seems to be.
right?
This is been.
Oh, it's a spin connection.
Yes.
Oh, okay, it's not. Yeah, I was confused, but because you use gamma and not omega. Right.
Come into a power matrix,
Right.
so epsilon.
Right. Okay, so it's spin connection, and this, so it's antisymmetric start.
Yeah.
Good. So then everything is fine.
Oh, let's see. One page. Right, plus. So these are Gauge invariant quantum function, quantum state functions. then the quantum operators. Yeah, this is also. Oh. 1, 2 here. Operators. That's 1, 3. The connection. In a connection representation, step psi of phase in some sense. Connections as operators take the multiplication. Of course, not by a component A, but by just by a matrix element of the holonomic operator. U, A, gamma, A, B. So here we don't mean the whole operator, but just one matrix element. For us, as canonical conjugate quantities to the connection, they are promoted to differential operators with constants, Planck constant, Gravitational constant, third power of the speed of light, delta by delta A by x, functional derivative, or this here we recognize, I think we should touch on minus. Recognize the Planck length. This is an operator valued distribution, and to get an operator, we integrate over some surface E AI x dx. And this gives a flux. Surface yes.
So what is it, the D2X?
Yes. Also, and then one form, we have the one form, the linear is the value one form, is integrated along paths. Here I forgot to learn some dx from the S parameter. And these ones, vectors, and we convert it into dualized, converted into two forms, are integrated along surfaces. And what we get is the so-called holonomy flux algebra. Well,
So I didn't understand. You dualize what?
the
Get the two forms.
EI with an epsilon that it has an
But the I is not the coordinate index. The A is the coordinate index, isn't it?
yeah, no, this is the triad. We also can just
I goes from 1 to 3, A goes from X, Y, Z.
yeah.
Right?
A also goes from 1 to 3,
Now it goes from X.
or from A, X, Y, or mu, or whatever.
Right, but it seems that A is the coordinate. This is a vector field, it's not the one.
It's a vector field, yes.
So how did you make
Well,
it?
this is epsilon. With epsilon by jk, and there are jk two antisymmetric indices.
Right, it's like in the algebra of the symmetry. Okay, so how did you make a two form?
Integrate. Well, it has two antisymmetric indices.
Yeah,
Well, two form.
well, not if they are SU2 indices or SU3, SO3 indices. I would agree if it's AD antisymmetry. maybe it's a true form on the group SO3 manifold, but
Oh,
what are you integrating it on? If you're
I take it, yeah, we integrated with the normal vector to the surface. Here you have a vector index and with the,
so can you make it more precise? So what do you
well,
contract it with? Then I mean, you're saying
well,
the I index is not free; it's somehow fixed according to the surface. Is that what you're saying?
well, if F is a normal index to the surface.
But now F has what is that? F. What is that?
A normal vector.
So, but it has, if it's a form, it has the index in the wrong place. Right? It's this is like a vector indeed. This is like a vector.
Yeah.
It's not like a form.
No, but in this way you can integrate.
The point is that
And
the E is a vector field.
Yeah.
The vector field it is okay, one vector field in dimension 3.
Right.
So there is this duality by Hodge that transforms me into a two form.
Hodge is not.
Much dual.
I mean, the vector field by the musical isomorphism can be transformed into one form, and then the one form by the Hodge into two form, and then integrate.
No, but then you need metrics.
Yeah, you need it.
So where's the metric?
The epsilon has to be. Yeah. I mean, then you have E, AI contracted with epsilon ABC,
Mhm.
and then DXB, which DXC.
Mhm. Mhm.
No, this way with this flux, you can construct an area operator. Well, the area is just a flux. Flux along the edges crossing the surface.
Well, it looks, I mean, is this integral supposed to be over a one-dimensional?
Well, a two-dimensional surface.
Right, but you're writing it like df. That seems very strange.
It's a normal vector to it.
I don't know. So that means.
If you integrate over a surface, you will down times tangent the one form.
So that then I would write it as the vector.
So crossing
Yeah,
two.
that's the same.
Yeah, but this
coordinate
doesn't
vectors
really
here.
make sense of the notation is strange.
You should not use a metric.
You don't need to build up some.
It has to be a
You
tangent.
can be fancy vectors and
I understand what you say. I'm just objecting to the notation. Looks strange that you write a two-dimensional in the surface as it looks like a one-dimensional.
something
that it's really. Yeah.
something
Trivial. That's the.
Sure. It's the DF. It's the DF.
One is.
Yeah, it makes more sense to write it in terms of epsilon ABC.
Yeah, it's like.
You probably
Contracted with E and the other two with the X.
normal vector to the surface.
Right, I don't write a two-dimensional surface integral as dn. That's not something that I commit.
Right.
No, I do not do that. I do not do that. That does not make sense to me to write a two-dimensional integral as dn. It looks like a one-dimensional in the direction of n, which is not. I would write it as Linus said, epsilon ABC, or like Giacomo said, epsilon ABC dx.
D2s or D2x?
Well, do it like Giacomo said, epsilon ABC, epsilon ABC.
And then
Still is not really correct, but okay, I understand. Well, I mean, you're just writing it dx, d2x. I don't know what the x is. I mean, x has to be. Yeah, doesn't matter. Doesn't matter. Doesn't matter.
No, this introductory models are finished. Then you come to a simplified word. Symmetry reduced model.
So far, everything was in 3 dimensions.
Yes.
Yeah.
We don't
There's no Lorentz in there, and
we don't need high dimensions, but it is split.
well, space-time
It's just like,
yeah,
cross product.
space-time is 4 dimensions.
Yes, it's yes.
Yeah, exactly. But how do you recover Lorentz invariant?
Well, then with the aid of the Hamiltonian constraint, you can think that this three-dimensional hypersurface into a four-dimensional manifold.
Right, but
If you, well,
if you make the split explicitly,
So,
in fact,
like,
you need
have a cross product.
some kind of flux, some system.
Surface.
right.
Oh, you mean this as a finite equation?
No, if you integrate over a surface.
I agree that it works classically,
I think
it's just equivalent to general relativity. But in quantum theory,
No,
you should expect Lorentz invariance to be broken.
you can also write general relativity in terms of symmetric in a canonical form. And split it in space and time and then construct
Classically, yes.
Hamiltonian dynamics or motion dynamics.
So I guess then the question becomes what equation should you check to check Lorentz invariance? You know, something like if you do like condensation, then you have to check some combinators.
Yeah.
To see that Lorentz invariance is something similar here. I mean, do you have expression for the generators of the Lorentz group, the boosts and things like that?
Generators is the Lorentz group.
The boost is broken from the
Well,
beginning.
No,
Yes.
But do you have expressions for those operators that would generate the Lorentz boost? Are they? Is it possible to write out?
the generators for special spatial transformation for spatial transport, with morphism constraints, and classical Hamiltonian constraint generates time evolution.
Right, but now some kind of rotation, like Lorentz boost.
Nice.
In the Lorentz, in the matrix step, we fix the first line as 1, 0, 0, 0.
Yeah.
Okay. So going to the algebra.
Oh, well, Lorentz boost. No, there are generators of spatial translations, generators of spatial rotations, the Gauss constraint.
Sure.
No, it's formulated in terms of this variables.
Right, so, but the original theory has more symmetry, so in the original theory, we had generators of boosts, which somehow should be present here, although not nicely represented, because we wrote this invariance. One could presumably write them down and check if they are fulfilled in quantum theory.
No, canonical general relativity is equivalent to the traditional formulation. You can formulate general relativity also in class theory.
You can certainly do some quantization, then you can ask, does the quantum theory have the symmetries of the classical theory? Or are some symmetries broken? And one symmetry that the classical theory have, which we like very much, is Lorentz invariance. If your quantization program breaks Lorentz invariance, that's something that you want to check. What happens to that? The invariance in the quantum theory is possible to retain it somehow.
Well, what does it mean? Lorentz invariance, of course, locally you can apply Lorentz transformation, but general relativity in a curved space.
I guess when Lorentz transformation, we mean changes of the Vierbein. Of the
Vierbein, yes.
Vierbein.
Yeah,
And the Dreibein is of course manifestly.
yes,
But I guess what happens to the fourth direction? So
Yeah.
which becomes unclear. So
this is not manifest.
yeah, definitely not manifest. But
No, sure. Hamiltonian strange, but I think you have
right.
time transformations.
Right. So
you mentioned that we'll be embedding them in a 4D hyperspace. Even then, you wouldn't be able to retrieve Lorentz invariance.
We formulated a theory on space like hypersurfaces, and well, time evolution needs a kind of clock.
Sure, but let's say you have two different choices of this hypersurface,
Yes.
and you do physics in one choice and physics in the second choice. But somehow they should be equivalent. I mean, you should get the same answer in some way. So how do you relate these two?
Equivalence is formulated by the Hamiltonian being a constraint.
Well, that's just the time evolution, right? But
Yeah.
how about the choice on the hypersurface? That's also a choice.
Yeah, but the method of applying the Hamiltonian. And if the Hamiltonian is a constraint, is that equal to 0, then all these possibilities are equivalent. I'll just gauge.
So how is the gauge transformation going from one choice of hypersurface to another choice of hypersurface, which are not just time translations of each other, but Lorentz rotations of each other?
Yeah, you would have a lapse function with, if you mean something like that,
Yeah.
a lapse function with, which is not definite, which is positive, and in one area in one place, in another place it's negative. If you take something like that.
Yeah, so that's.
I think it
Seems like a possibility. So Lorentz
positive
invariance
lapse function, you can consider different time evolutions, but if you consider something like that, which goes like what here, and Well, that's functional different sign.
So the Lorentz invariance is some rotation between the constraints, or what?
But I guess it's to somehow satisfy causality, at least locally.
Sure.
So I guess that
It doesn't go, time evolution doesn't go backwards. It's just,
And the consequence, the Lorentz invariant is constant of the actually being invariant under Lorentz invariant, and invariant under Lorentz information, right? I mean, the equation almost has to be the same.
Yeah, we can.
well,
Now, in the Hamiltonian formulation, you have the difference and the Hamiltonian.
Yeah.
All of these involve only triads. So all of these are invariant under only the rotation, SO3.
No,
Okay. So actually, I don't know what you mean, but you don't need boost, you don't need
no, for
check.
why don't?
Lorentz transformation, you need a time.
Because you fix time. So you are just forming the hypersurface, and so you need only SO2 or SO3.
No, and we don't have time here. We don't just don't use this.
Well, I mean, sometimes you would like to check if the symmetry group is the same dimension.
With the Hamiltonian constraint, we have all sorts of histories. Not one, not any history which out to depend on that. I think time, so we can formulate Lorentz transformations. But we would have to define a time, to fix time by some other system.
Right. But I guess you could have the time, and I guess you could introduce a lapse and a what you call shift function, and but of course this will now change in some way under these transformations.
At this point, we need only the space line factor, and then I think with spin format, then you form a kind of evolution where you can check the invariance under the Lorentz.
Yeah, and if you formulate this parameters, general relativity, the action function, the Lagrange, the Hamiltonian, the time evolution generator simply turns out as that constraint. It is a constraint, it's equal to 0, and so all these possible time evolutions are considered as gauge. So there is no time background. Somehow comes out or is defined by some clocks, by some field which spans an interaction, space time with space.
Maybe let me ask maybe a related question. In your very first sentence, you said that now you will present canonical quantum gravity.
Yes.
What is another look quantum gravity which is not
covariant loop quantum gravity in terms of
covariant.
forms.
Okay, and is that Lorentz manifestly Lorentz covariant?
It's four-dimensional, but no, it doesn't use the Lorentz group as gauge group. The technical problem is that the Lorentz group is not compact, so this makes things more complicated. If you took the Lorentz group as gauge group, it's I haven't seen the details, but it's much more complicated because it's not compact.
Yeah, today is exactly the point where the money comes of the variables where
instead of the general linear group of general relativity, you just promote it into a switch which is compact. I mean,
But the spin form formulation is that you have also spin networks in three-dimensional space, and you add one dimension. So from edges you get sheets, one sheets, from vertices you get lines. Also, it's not formulated with the Lorentz group as the H group.
we can go forward to the west.
Well, in this spin forms, you consider mostly closed three-dimensional surfaces or hypersurfaces, and where the bulk you have the spin forms, and consider transition probabilities from one spin network to another one.
So what is the operator that takes you from spin network to one spin network to the other? Whenever you have this ADM formulation, you have that from surface to surface, you can just move from them by using the Hamiltonian constraint, right? And whenever you have spin network,
Hamiltonian with a certain abstraction. Or shift vector.
but in theory, there should be some operator that takes you from spin network to spin network or something like that. I mean, like basically,
It's just in one dimension height. Yeah, but a three-dimensional hypersurface, surface as initial hypersurface and the final one. And in between them, a four-dimensional spin form. And then you can calculate probabilities, transition probabilities.
but is there any physical quantity associated to, let's say, this is an analogy I would like to have in mind, like whenever you have the idea, you are creating the space, and whenever you move from hypersurface to hypersurface. But what is the thing that you are getting whenever you move in spin network space, if it is allowed to, I'm allowed to say like that. Have a spin network,
Yeah.
then you go to another, then you go to another, so that movement in the spin network space does determine something physically for you? I mean, a physical quantity or something?
No, you can consider the probabilities of different spin forms between them. This is four-dimensional spin forms. And then you get a probability for one spin network going to spin network function, going to another one.
I believe also the related volume and the area associated with the link of the spin network. Because it could be in a different representation, so carrying a different volume. So.
But then you can define like an area operator whenever you move from spin network to spin network or what? Can you define an area operator if you go from one spin
No,
network?
you just calculate the area at every time. So the area of a link, the hypersurface, and then the area of another link, and the next hypersurface. So you have some probability of moving from one spin network to another.
Yeah.
So you can calculate the area of the initial one, some link, and the area of another one evolved. Okay, so you see that the area of space could change over time. And then there is some physical there is additional application for it. So for example, if you have a tetrahedra with certain volume and then evolve it like a gimbal, you can get a different volume. So contracting volume.
So in the old variables of ADM,
In the end, you cannot.
no, of course, but that is an end because ADM, I mean, the thing that Franz is describing is like the improvement of the ADM formalism, isn't it? Because we're basically introducing these obstacle variables in such a way that you get an two kind of gauge theory or a formulation of gravity in terms of if you want to see a gravity as a gauge theory, something like that.
Yes.
So, but in the old approach, before you introduce those variables, you have these hypersurfaces that the evolution will basically give you the Fourier space-time. And I do not know what is if there is any relation between this spin network you are introducing now and some other stuff that you were like previously having in the ADM formulation. Or the spin network were introduced with the purpose of what? That's my idea.
No, the input was introduced to get one. Classically, the formulations are equivalent. You can formulate canonical theory in terms of symmetric and the conjugate momenta. That's essentially also connected to the extrinsic curvature, or in terms of this spin connection or article connection and triads. Classically, it's equivalent, but when you want to define quantum functions or wave functions of the connection, then the problem is that this is gauge variant. If you change coordinates, the connection changes in a non-homogeneous way. You get some additional terms, and so the first idea people had to take closed loops as a trace. So not to take a x autonomous, the transport, parallel transport around closed loops. For this reason, it's called to this day loop quantum gravity. And in the next step, loops can be combined into spin networks. So the reason why spin networks is to get rid of the gauge dependence. And so you get some discreteness. You get I say only just loops where you get connected them into a network, and so some discreteness.
A bunch of loops will give you the structure of a lattice or something like that, in such a way that you compute area, and therefore you can compute, say, entropy of black holes or things like that. So the basic thing that you are saying is you have loops that loop quantum gravity, and then you do some weird arrangement of loops that are the spin network thing.
And while outcome of this is discreteness of area, also of geometry generally, of area, of volume, of length. Because if you take some surface, then the area is just the flux of the spin network. So you can have one edge or two, and so on, and each one has a representation. And the area, the physical area, the geometrical area of this is given by the contributions of each of these representations.
Does that recover the classical area?
Does
that recover the classical area?
So you get, well, we take a classical limit. Perhaps in terms of discrete numbers. So each such line with representation J contributes J plus 1 Planck length squared, or maybe the immunity parameter times Planck length squared. So you have a discrete spectrum of area. It's not even at the coordinates, but
Yeah, here you can record it in the sense that you can partition your three-dimensional space so that it's a sum of a huge number of little areas. Okay. But the point is that how to relate these quantum areas to classical, because classical one is something that you can observe. Okay.
Yes.
But the quantum one is actually how can I say, like, it's not fixed because you don't know the representation of each of the links. So it means that you have a huge combination of those. So you don't know actually the single contributions of each.
But shouldn't you just say, okay, I'm starting with this, ending it with this, and then you sum over all spin networks, which has this starting and ending. And for each, you check at some point the area. And then you just say that the classical area is the area where there are most spin networks that contribute to that particular number. That should be some.
spin networks.
So there should be some kind of classical path between them where you have more spin networks that look the same somehow in between. The same.
Yeah, we still don't know. But one thing is that most of them has to be in the fundamental, in the ground state.
You will have a huge number
Yeah.
always. And the following Feynman's formulation of quantum mechanics, all of them contribute some complex number to the probability after some number. So,
This is possible.
and somehow the classical thing should be close where you have most contributions to this. Where you have contributions which widely oscillate and doesn't contribute, so there should be some kind of middle road where you have some. But it's not clear that it makes sense fully as a classical.
It's not clear that there exists a semi-classical.
But, and of course, you know, that if they have many networks have the same area, maybe they have widely different, some other observable. I don't know, they have to have this, to make it classical, there have to be more things that sort of agree along the way, right?
No, you can have a,
If you measure the fixed time, the area of something,
Yeah.
so you have the contribution from all the links of the spin network. You just sum up all the contributions of links.
no,
But
you just identify.
You don't know the number of the links.
well,
Is there some kind of H-bar loop expansion? Can you say something about what spin networks that contributes most in the classical limit? Like, for instance, for Feynman diagrams, we know that it's three diagrams that they contribute most, right? Or would there be something similar, a semi-classical limit of networks that would be most important?
I know that one.
We can also have superpositions of spin networks, so then you've got the sum of the contribution of the spin network.
I noticed that you paired H bar with the Newton's constant G.
Yeah.
Does that lead to another?
Planck.
Yeah,
Planck,
right. So
Maybe that's the point, if you get some kind of thing multiplied by powers in Planck.
right.
No.
Yeah, so it's definitely the Planck length rather than the Planck constant.
So each such link contributes something, a few Planck lengths, this number times the Planck length squared. And then of course, there's a macroscopic surface and it's a huge number, and you don't see that it's discrete, it's practically almost continuous.
But to even talk about an area, you have to have a classical limit. I mean, I agree, it's sort of, it vaguely looks like this should be a measure of the area, but if you don't have a classical limit,
Don't have one.
if you don't know how to take a classical limit, what does it mean to have an area?
This is actually a huge issue in local.
Area is not right. No, the area is not given in terms of coordinates here, coordinates, no real meaning.
Right.
It's just given, well, coordinates fix an area. In terms of coordinates, I mean.
That's not quite the question. I mean, the question we're asking is similar to say, well, the position of a particle is also something that is classical. There has to be a classical limit for us to be able to talk about where was the particle. Position is something which is classical. The quantum description of a particle is that you sum over all paths given an initial and a final point, and then you sum over all paths. So then you could ask, where was the position of the particle? It's not defined unless there is a classical limit where there's a classical path where you can say, well, yes, it's here classically at that. So there has to be in your sum over all spin networks that connects initial and final spin networks. There has to be a limit where somehow almost all of the spin networks contributes in the same way.
Yeah, right. Expectation value of area. If you do this.
Right, and that expectation value should be very centered around the two points. Otherwise, there's no.
For large number of closets.
There is no classical area, but it's not clear that there is such a limit. That's the point. Right? I can take the average of these two positions, it's in here, but it doesn't mean that the particle. So it's the same thing. If you have the sum over spin networks, so from here to here, there has to be somehow a large number of these possibilities that all have the same area, more or less. And then we have a possibility.
Well, for macroscopic areas, I think that's clear that comes out.
Well, it's not clear. We don't know. Can you give me all of this spin networks that go from one particular, let's say, macroscopic?
Well, this may not be the case. It's just a black hole. This forms itself, and maybe the area around it changes rapidly, and for a large, maybe there are large uncertainties. But in our case, where we have a small gravitational field.
Right, but there's
what does it translate to? Yeah, what is the calculation you should do to recover some small correction around flat spaces?
Yes.
Suppose I start with a flat space and evolve it using the spin network. What do I get? What happens? Are areas changing? What's happening?
right.
I mean, that's something we can.
Then there should but then you have to make some kind of organization principle of all possible spin networks so that you can start counting them and figure out that there is
Right.
some
Yeah,
kind
you
of
need to be able to define some kind of semi-classical.
So there are no emergent phenomena from microscopic description. There are no new emergent phenomena from microscopic description. It's completely independent of what's happening, classically speaking.
Well, yeah. So it's hard to talk about fluctuations around the classical.
Yeah, I don't think you can answer the question.
Yeah.
So the classical limit should be that the Planck constant goes to 0.
No, so it means that the Planck length goes to 0.
Sorry, the Planck length goes to 0. Yeah.
No, but only if the area is large, you don't see discreteness. One length is very small, and then
Yeah, oh, right. I'm thinking in the same way that we treat
yeah,
h bar as a parameter rather than a number. Then in this analogy, we will treat Planck length as a parameter rather than a number. And then, I mean, of course, has some value, but we want to know when we're talking about that we are taking a semi-classical limit, then we're saying we're taking that this variable LP going to 0.
Should make sense if it was dimensionless, but
Right.
it's dimensionful, so it's problematic.
no,
Right,
But we have to compare it to something.
Yeah, but if we're doing the same with h bar, right? That's also dimension.
no, it's simply very small in comparison with millimeters.
I understand what the actual value is. I'm talking about that often in theoretical physics,
Yeah.
we are not treating as a number, but as a variable. I do that.
Well, later on, I had the problem with rather large length fluctuations in the first attempt.
Okay, yeah, so maybe we should continue
Yeah.
and see on some concrete solutions, which maybe is easier to understand.
Then, yeah, you can present a simplified, a symmetry reduced model. Comes from derived from a cosmological polarized Gaudi model. We should formulate in terms of graphical variables by energy and date in the first decade of this century. We have the metric. It's what I've written down here. All the functions are assumed to depend only on P and Z, so it's in the directions of X and Y, everything is homogeneous. So we consider plane waves. It's taking over from the old model, but here we consider that it's not a reverse or a sphere, it's an open model, and it's from minus infinity to plus infinity. Everything depends only on E and the dimension. It's a great model. We have the client. One. X. One. Two. Two. I will go with a notation from energy and date. The third one is denoted by 3. 3. And the connection is given by A1 X1 A Y1 A2 A 2, AI2, and another component A, which is a Z3. Yeah, here in the polarized model, it turns out that the spin connection doesn't appear neither in the diffeomorphism constraint nor the Hamiltonian constraint. So it's convenient to take here simply the extrinsic curvature part derived from the extrinsic curvature in the direction x and y, for 1 and 2. And now, of course, the Poisson brackets are A, Y, E, J is equal to K, AI, E, J, because the spin connection is formulated, if the negativity connection, it can be formulated in terms of the ease. So this has 0 Poisson bracket with E. And yeah, here it's just more convenient to take here just this part, the extrinsic curvature part from the connection, because just thanks to the polarization model and polarization condition, which makes the extrinsic curvature diagonal, acts in this way that the spin connections x and y here do not appear in the theory, in orthoformalism, neither in the diffeomorphism nor the Hamiltonian constraint. And from this one you can extract radial variables.
What does it mean that it's cosmologic? Polarized cosmology, what does it mean? Cosmology?
Here, how we construct cosmological models.
In what sense? Cosmology? You said it's a plane wave, so what is a cosmological wave?
Not a cosmological model, it looks formulated. This maybe is taken over. If it was not a model for a torus, instead of that, it has an angle and it's closed. So you should just open it up.
So it's
And everything depends only on E and Z and you have plane waves.
sure, but I was asking about it before. So this is not cosmological, right? It's just a name that you took over from.
Maybe now we construct cosmological models.
Right, but
Now
now it's not.
this one is just taken over.
Now it's not cosmology.
Yeah. We just want to describe plane waves. So we're everything in x and y direction.
And is this a vacuum solution?
Yes, it's a vacuum solution today. So we have Ex. Ex1 squared plus Ex2 squared. And the radial parts. Ey. E1 plus E2 squared. And we don't change. And then we have also AX. AX1 squared plus AX2 squared. AY.
In the Poisson brackets,
Better than K.
in the Poisson bracket, what happens to the third component? There is
No,
no.
this also.
These also, so they are not part of that, that I and J are not three,
A and E.
like it was.
So canonical.
So you change the notation a little bit. So A and I and B and J are now only 1 and 2, and the Z are separate. The
Yes,
third
yes, these are 1 and 2, and this is 3.
So it's
I just move it over from.
And when you say the canonical, they're equal to some delta function.
Yes.
Canonical.
Yes.
Yeah,
I will understand that X and Y. You look at that.
Yeah.
I'm just saying that you change the notation from what you had before.
Oh,
So,
yeah,
yeah,
I should write. I should write K. And we have A, which is not, doesn't change. It's a regular, it's the same. So these are radial variables. There's also an angular variable, but it is taken care of by the Gauss constraint. The polarized model means there would be still an angle, a gauge rotation around the z-axis. And this is already taken into account, or already, this is already fixed by imposing the Gauss constraint. It doesn't appear here anymore. It fixes the rotation so that we are left with these radial variables. So we have the 3 canonical degrees of freedom. Ex, y, kx, ky, a, which describe the dynamics. The system is homogeneous but not isotropic in x and y, and yeah, in terms of when speaking about gravitational waves, plane waves, E is called the background factor. It describes the transversal cross-section area. And so the degree of freedom is that this can be larger or smaller, it can oscillate a bit. This is the background. And this the logarithm of this ratio is called wave factor. This was formulated in the 60s by Ehlers and Kuhn for plane waves, but they took here only one. They didn't take into account the possibility of longitudinal fluctuations from the beginning, because all we know classical gravitational waves are not longitudinal. Just with these two notations, background area and background factor and wave factor. So the wave factor then describes such fluctuations. When you have a ring of particles transversal to the gravitational wave, maybe you can observe something like that. And we have still longitudinal fluctuations, as it will turn out. So the classical model. When quantum states and operators spin networks, in this case, are one-dimensional along the z-axis. That's just a string of edges and vertices. E, and so on. Then we construct edge homonyms. Parameter, integer parameter, integral I. And such is very for a normal normal holonomy along the edge as we have it in general theory in full loop congruency. And then at the vertices we have time holonomies. With weights in holonomy taking weights to y direction. And lambda b to y and r x and r vertex and n r and then at each vertex we have a function m, which is the tensor product of these holonomies. And they are only phase vectors. Say y or numbers coming from all are just extensive curvature. So we have this means that each group is reduced to U1. Thanks to this symmetry reduction.
Is this a choice? Or,
Well, we just have this.
yeah, but, you know, to me, it's not clear that this is what we have to have. Could you have arbitrary representations here? If not, why not?
In analogy to a full theory, we will construct connection operators. In the general theory, we have connection operators multiply state functions by matrix elements of the holonomy operators. Here the holonomy is only a phase factor, so we can just multiply with the whole phase factor. And if
It looked like you won representation theory. So you won is probably the
and with the
surviving.
Yeah, but why couldn't everything be like in holonomic representation? You can still multiply things, everything seems to work. You don't need any vertex factors, you just have, you know.
In one
SU2.
SU2?
Yeah, SU2 fundamental.
But yeah, okay, so I guess SU2 somehow is reduced.
Yeah, but why? Is it a choice?
Because nothing depends on X and Y. No?
So yeah, we have only the one. There's no space for this. This is on 3 or
So maybe it's like you say, like I mean, it certainly has to be. You made the radial variables by using, and then there's situations. So
Yeah,
there's something like that.
broken explicitly by the choice. Yeah, more.
Yeah, the
So
full
that's
SU2
strange.
is probably broken.
Yeah.
And there's surviving U1.
So you are explicitly restricting the type of solutions that you're looking for, that they will never have any fluctuations in X, Y
No,
direction.
we cannot rotate in the X or Y direction.
Right, but this is your choice.
That's just a symmetry reduction. That's we are also saying.
Your choice. I mean, in real life,
Well, in real, that's no infinite plane waves.
So, yeah.
No, that's a simple reduction. Well, then the operators, the connection. Or would be multiplication by matrix elements of holonomy operators. So here we have only these holonomies, so we can only multiply them by these factors. This is the only matrix element which we want to stay with. So i.e. I have kx, e to y have ky. These are the lowest order representation of fundamental representation, so to say. And so e to y of integral e a d z. Or more concretely, in terms of sign functions. So k, x or y is 2 sine k x r. And anyway, we don't need this. This is 2 sine half, and again this integral. Now we consider the action on such states. The connection operator kx when it acts on state m is 1 over I from 2 sine, where e to I k x half minus e minus I k x half e to I n half kx. So here m becomes larger by 1, here it becomes smaller by 1. So what we get is 1 over I n plus 1 minus n minus 1. So it's a combination of a raising and lowering operator. And of course, a, y, analogs, and also a. So this corresponds, the multiplication by this two, or by this sine function corresponds to the multiplication by a matrix element in full theory. When multiplied by two failed factors, in the limit the kx is small, this goes to kx even for the y.
So why did the faces get replaced by signs?
Why?
I don't know.
Well, as I just said, in the limit that this is smaller, when you can also multiply, introduce here a small parameter. And then this becomes the limit of something very small, this becomes approaches kx over y, or then with this.
Okay, I'm not sure what the equation means. Kxy is equal to 2 sine kxy over 2.
Is it
It
really?
agrees for infinitesimal. It's fine, but
Yeah.
You write it this way, and then it acts.
Before.
Yeah,
But so what does the equation mean?
What does the equation kx from y is 2 sine kx from y?
It was say,
Yeah, actually, yeah. Or maybe I should write it in this way. The operator. Yeah, is equal to.
okay, you mean the action by something. And for some reason, you're taking the signs instead of the phase factors.
Yeah, we have
Because you want something trivial or?
some holonomy or some combination of holonomies. We can directly multiply by the connection. This doesn't make sense. This gives again, this would give again gauge variant state function. It's a multiply, just simplify the connection. It's not the holonomy anymore.
I guess maybe it should be understood as a sub-representation, that instead of working with the full kx, y, then we can combine operators into a certain combination and then
Yeah.
closes on itself.
Yeah, it will also break minus. Also, the one will drop out here when you expand it in lowest order. But it's something in lowest order. It should classically, well, this expression in lowest order should be a x and y, x or y. Well, if I make it y operator. Ex is e plus square integral delta by delta a. For my interval, I now here from the one dimension, phi is an interval with a vertex with theorem. Well, if this acts on such a state, you just get down in half, and you already have e squared. So e equals m is 1 p squared times m, and in the future, we will set 1 half p squared, or maybe with the immediate parameter equal to 1.
What is the integral of which integral is that?
So all the three axes. So we have the vertices.
So this,
Some intervals containing the vertex.
so it's the integral of z, correct?
Yes.
So what is the area that we're measuring? Where is?
Yeah. This area, because we have n squared. If we have x y z, then ex is an area of for these areas. Ey.
Okay, so now I see the interval is the one along the z, the side along the z-axis.
And E is the transferring area. And together, the volume is given by E equals 1. What means on the different metrics is So I think that's all what I wanted to present, which is taken over the general quantum gravity and then this model, where they formulated for this model the constraints. And yeah, that's essentially all there are two papers. One present the classical model, the second one quantum states and constraint operators. And now I can, it's enough time just to present what we have been doing. Yeah, so that we can please make use of something of that I've written down here. So, wave propagation. I wanted to, well, we wanted to formulate propagation without dispersion. And exactly the previous slide. And then see if it's possible in quantum theory or isn't it? Is it not possible? So this, the idea is we could describe this as the existence of a null killing field in the z direction, positive or negative. Existence of null. Plus minus d direction. One, the killing conditions. We have a killing vector field and the associated covector. Covector, a u is k 0, and plus minus ex dy divided by e. Okay, so here I have to do again this metric. When we take this square times the inverse metric, we get 0. So k mu upwards is equal to 0. So, so the first two killing equations, 0, 0 is equal to k3 equal to 0. It rise to integrability conditions. And beyond one integrability condition, quite nice looking formula. And prime over the square root of g CSV, that's this. times the z derivative is equal to the square root of g to z differentiated with respect to t divided by n and once more differentiated. So here we have time and space relations, and the remaining non-trivial Killing equations k22 equal to k11 equal to 0. Well, the Christopher symbols which appear here, this gamma 220, gamma 110, which contain time derivatives, are expressed in terms of a extensive curvature where KAB or K is diagonal KAA is equal to -1 over n or 2n or 2n G AA 1. So if we do this, if we make use of this gamma 2 gamma 110 in this form where this derivative appears, we find these two conditions. This comes from K11, which is equally into more convenient and more closer to a physical interpretation of this form. We take the sum as a difference. Then we have the sum of this plus this and this. Subtract the difference, here is difference, and this. This is just the first one says the space derivative of the background factor is equal to the time derivative. This is, when you take this into account, this k, the k contains time derivatives, gives the time derivative of the background. And here we have the z derivative of the weight factor. And here, this is the time derivative. The time derivative is the factor. U plus minus is equal to 0. Time derivative of E and logarithm E y divided by dx is equal to so you can see the physical meaning in this form. Now, this is an example where we have space and time involved, and here the time dependence or time derivatives were formulated in terms of the extrinsic curvature. So we are again on the hypersurface. We don't have here explicitly time derivatives or time or even no collapse function. We just get relations in the trimer and here the connection variables. No, and when these are satisfied, then also From this follows the equivalence of the Hamiltonian and the diffeomorphism constraint when we choose this square root g z as Lab's function. From this follows that Ex Ey divided by H plus or minus is weakly equal to 0 up to these conditions and so when these conditions are satisfied and they are equal to 0, then this becomes equal to 0. So time evolution with a choice of the unit of time being equal to the unit of c is equal to spatial derivative or spatial transport, which one should expect from the existence of such Killing vector fields. So, but these are the classical conditions formulated in terms of Killing vector fields. And formulated in quantum theory.
I don't know how long will it take because there is a teaching afterwards, so
I know.
at some point.
I know, yeah.
Even
Okay, 3, yeah. So we should finish now.
I mean, it's up to you. If it is quick, you can just say, or we can just finish next.
Yeah, of course, because there's a lot to continue next week. Well, let me say that how should we implant this quantum theory? If we take such a sequence, edge, a vertex, and edge, and consider this, it acts actively or non-trivially only on the vertex. Here we have raising and lowering operators. On the edge, it acts only by multiplication. So we take such a sequence with V, K minus here, we take just two holonomous, K minus and K plus. And at the vertex, well, we have a superposition of such, well, here we have and holonomies. So this, the first, the U class acts here on the vertex, with the two edge levels as parameters. Here on the right hand side, we just take the difference, K plus minus K minus. No. Yeah, I formulated, I don't know, finish. We introduce E coming from background, K plus minus K minus, and then and formulate U plus symmetry. This means we write Ex, Kx as a square root, Ex plus square root of Ey, Ky, Ey plus, well, plus E prime. And then when it acts, we have to clear now. and acts on a state M here, first we get the letter M, then here we get one, we get the state M plus one minus N minus one, and then M plus one multiplied with the square root of N plus one, and minus one, and multiplied with the square root of N minus one. The same here with N, and here it's simply multiplied by this B. And the psi V is superposition M, N, 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 N. We get this difference equation. This difference equation comes from U minus, and this is one solution, it's U plus. I write down this once more next time. So maybe let's find the image. That's approximately 5 pages from 14. Thanks so much.
It's great.
Yeah, still good questions.
Okay.
So,
No, maybe for master training,
They enjoy.